Welcome back to Nature of Code in Rust and GGEZ. We're moving on to example 2.4, including friction. So if we take a look at our examples here, we have our bouncing balls on the left here that has no friction, and on the right that has friction. Now, there's a little bit of glitchiness going on. I don't know if it's because I'm running in Firefox or something else. But that is in P5.js. We're going to be doing this in Rust, and so we shouldn't have any of that glitching. That's actually something I can see. It's not just artifacts being captured by OBS here. So the general idea that we can see is we want our balls to stop. Eventually, basically friction is slowing them down. Now in this case, friction is being applied to both air and ground, basically just all the time they're getting slowed down. Let's go ahead and see what we need to get that working. So if we run right now, this is copied from the last example, 2.3. We'll notice that this is not really bouncing that high. I actually did a little bit of troubleshooting off screen to sort of like figure out what was going on here. I believe what's happening, a couple things. So first of all, let's come up here. Let's set our minimum 1.05. That should be good for mass. Our mover, our X position, let's start everything in the same exact location. So 0.0, 0.0, so top left corner for our location. Pass it into max and context. Everything else should be fine over here. And in the mover, I want to see, all of this should be good. But I want to make sure that our top speed is high enough because I think it's actually going a little bit too fast for our top speed. So if we make it 100 and then we rerun this, now everything sort of bounces at the same, much nicer rate than we saw before. Perhaps that's a little bit too strong of a gravity force. So we can make this, instead of a 1, we can just make this like a 0.1, for example. Maybe like a 0.3. And there we go. Okay, this is a lot closer to what we were expecting. So now that we have this in place, we want to apply a fiction. So as a friction, not a fiction. So as the book was talking about, we need a coefficient of friction for ourselves. I'm going to create that in our main library here. We don't necessarily have like any kind of physics system yet. That is something that we can potentially look into for this. But until then, let's go ahead and do it sort of like how the book has us doing it. We're going to create a coefficient of friction, and you're going to be at 32 coefficient, and we're going to make this 0.01, which is the same number the book has. Now, I don't know if that's appropriate for this simulation, but we'll find out. Then down here in update, we need to actually create our friction. So first of all, because we can't access self inside of this this for each loop, we're going to have to grab that coefficient outside of here. So let coefficient friction is equal to self dot coefficient of friction. Okay. The next thing is, so we have that. We need to get a clone or a copy of the velocity. Well, we can't do that right now because the velocity is private. So I'm going to go ahead and make this public. And now just in here, we can now grab that out. So we're going to create a mutable friction vector is equal to the mover dot velocity. The mover is a reference, so we can, nope, we don't even need to destructure it. We now have the vector too. Then we need to multiply it by -1 to reverse the vector to make it pointing in the opposite direction that we're moving. So that can now be friction times equals negative 1.0. We're also going to normalize it. And then finally, we need to multiply it by that coefficient of friction to like make it really, really small, to scale it down. And then we can apply this force. And that should be enough to apply a friction to the balls as they're flying around the screen. Let's go ahead and see if it works. And we should see them slowing down over time. Now this seems to be really slow for us. Now they're bouncing less high every single time, and we can see that the lighter balls are actually slowing down faster than these heavier, higher mass balls. So what we want to do is potentially increase that friction amount by just a tad. Let's increase you to like 0.4 and rerun this and see what the effect this has. We can already see that some of these that have like the friction affects the mass very differently, which is very interesting to see. But we can tell the friction is slowing these down quite a bit, which is what we were hoping to get. So that is example 2.4, including friction. I'll see you in the next video. Have a great night and see you next time. Bye.